fell swoop, which is how I do it. It's kind of like how you do taxes, you know, like if you buy something for $1, you know, how much tax do you pay on it? And you multiply it times 1.07, and your price will be $1.07. You guys ever do that? With your taxes? Okay, that's the same thing here. So you basically, by multiplying times 1.07, you went up 7% to calculate the taxes in Petaluma County. Well, if I wanted to go up 30%, I would multiply times 1.3. No, not 0.3, because that would only be 3%. So it'd be 1.3. You do it all in one step. So that's how I do it. 50 times 1.3. Lo and behold, through the mysteries of mathematics, we have done this in one step and still got the same answer. I don't care how you do it, as long as you come up with 65. You don't get it off your neighbor's paper. Okay, what if I wanted to go down?
Just subtract it.
Yeah, I would take my 30%. Let me see. Does everybody have that? I just rewrote the new technique right here. So the new technique would be 120 kVp and 65 mass, and my film would be visibly darker. Visibly darker. Everybody has that? I want to go too fast. Okay. Now here's another example. How would you change the following technique if you wanted a minimal visible decrease in image density? Minimal visible decrease in image density.
Multiplied by 0.7.
0.7, that's right. That's what you would do. You would multiply by 30% and then subtract that from your mass, which this is the long way. Or you could do it all in one fell swoop and multiply 250 times 0.7. And by golly, it would give you still 175. So like I said, you know, either way works for me. Math really doesn't get much harder than that. I mean, the next hardest thing we got to do is actually square something. So the trick is just being able to determine which formula to use. That's the hard part. You're going to get several formulas here right in a row. You just got to be able to pick out the right one.
Would that make the film lighter?
That would make the film minimally visibly lighter. Yeah, and that's hard to think that way, but that would be the minimum amount of change to make your film just light enough to see a difference. What if I wanted to make my film twice as dark with mass? What would I do? What would I do to this one? Twice as dark with mass. What would I go to? I would double the mass, wouldn't I? If I want to make it twice as dark, so I would go to 500 mass. If I wanted to make it minimally visibly darker, I would go up 30%. If I wanted to make it twice as dark, I'd go to 500. What if I wanted to make it half as dark? Where do I go to? 125 would be half as dark. Okay, half as dark. Okay. Ooh, boy, we're almost done. Cool. And just in time. You know, every year during this class we have this little picnic thing outside. So I always have free lunch today. Inverse square law. Oh, I have it written down. Okay. And that's it right there. That's a mouthful. There's really no easy way to memorize it other than just memorize it. You know, one day, like the light will come on, and by golly, it will actually make sense to you. That usually doesn't happen until Imaging 2. For some of you, you'll get it now. It's kind of a very abstract kind of a formula. But it reads like this: the intensity of the beam, which is, intensity is what? X-rays, quantity of X-rays. The intensity of the beam is inversely proportional to the square of the distance between the source and the image receptor. That makes absolutely no sense to you. I hope it doesn't. We'll shed a little light on this thing here in just a minute. That's actually a formula. That's a formula. So this is the word version of this formula. Okay. You see where I have MR up there? If I was going to measure the distance on something, I would have to have a unit for it, and it would be probably a meter. You know, that's like the standard unit for measuring distance, the meter. If I wanted to measure time, the unit would be a second. If I wanted to measure how many x-rays are coming out of an x-ray tube, the unit is called a milliröntgen, MR. I don't want you to know anything more than that right now. MR is just a unit used to describe in quantity x-rays coming out of an x-ray machine. I'm not going to ask you that. This is really a different class. I'm not going to ask you that. But that's when you see MR, that's just how much dose you have. Milliröntgens. We'll learn all about this in radiobiology in the fall. Okay. So now what we need to do is we need to take this formula and we need to take these words and convert it to a formula. And this is the formula right here. Well, let me see where I have the formula. Right there. This is an indirect relationship. The inverse square law is an indirect relationship. And I think that's probably a good thing to firmly entrench in your mind right now. And here's how it works. It's all about distance. We are talking about the distance from the x-ray tube to the image receptor. That's what we're talking about, is that distance. What distance do you use for a chest x-ray? 2 inches. What distance do you use for a KUB? 40 inches. There's a difference in distances there. I have to adjust my technique according to that difference in distance. If I was to take my x-ray tube and move it from 40 inches to 72 inches, okay, I'm going to move it further away. What's going to happen to my density on the film if I left everything the same? Is it going to be darker or lighter?
Lighter.
It'll be lighter. Okay? It will be lighter. If I move my tube further away, my image will be lighter. And the reason it's lighter is my beam intensity at the image receptor, beam intensity is going to be less because it's further away. It's further away, so it's going to be less. Think of it as a shower head. Think of the primary beam as a shower head. You know how our shower head kind of goes out like this? Okay. Well, what if I was to take that shower head or the primary beam and back it up? What's it going to do? It's going to continue to spread out more and more and more, wouldn't it? Okay. The further away you brought it, wouldn't it spread out more and more? So one individual little spot at that image receptor, that beam intensity is going to go down. So when I move my tube further away, my beam intensity goes down. If I move it in closer, my beam intensity goes up. What's going to happen to my density? That's going to go up. Okay, it's going to go up. So this formula is used to adjust beam intensity for new distances. So if I, for whatever reason, needed to shoot my KUB at 50 inches, how would I know what technique to use? Okay, that's what this formula tells you. It will give you the new mass that you would use at 50 inches. It would take the mass that you used at 40 inches and it would convert it to a mass that you could use at 50 inches. And this is it right here. I don't like this formula. You don't have to use it. Maybe you like this one. I don't know. You can use this one if you want. I prefer the next one that I'm going to give you. For me, it's just easier. But here's what we do. We are going to take our old mass, which would be the mass that we used at 40 inches, and we're going to place it here. then we're gonna take our new mass, which we don't know, at